So, hi everyone, I'm Maddy Bowers, and today I'm going to be talking about some recent work on leveraging probabilistic programs to help speed up the synthesis of deterministic programs. So the kinds of programs we're going to be thinking about come from the study of concept induction, which is the ability to learn a new concept from just a few examples. So this is studied both in AI and cognitive science. So in AI, for example, the abstraction reasoning corpus, or ARC, is a popular benchmark where the goal is to figure out the transformation that maps one of these input grids to an output grid. And over in cognitive science, there have been many instances of studying this, including these tasks, for example, where you're given an input list of numbers, and the goal is to figure out the rules that are bringing those input lists to output lists. So the rules might be something like this. And if we're equipped with a grammar over the space of programs, then we can write down solutions to these tasks as programs. For example, this is one that indexes into the input list, and then, it indexes into the input list specifically at the position given by the head element. And this second one doubles all of the odd numbers in the list. And so in general, our goal in synthesis is to find short programs that explain what's going on here. And we can formalize this as Bayesian program synthesis. So Bayesian program synthesis formalizes concept induction as a posterior inference problem with a generative model that looks like this. So we have our programs drawn by some broad prior on programs, like a PCFG. And after generating a program, we then execute it on our input-output examples, or rather on our input examples, and that's how we produce the corresponding outputs. And so the actual problem here is we're given some input-output examples, and our goal is to navigate this space of programs to find the actual high posterior ones. And in particular, this likelihood we have is extremely sparse. So it's only going to be non-zero for programs that agree with all of the input-output examples, right? That produce all of the correct outputs, that is. And so this is a tricky problem, but a classic approach to starting to tackle it is framing it as MCMC. So in particular, there's a subtree resampling approach people use with programs quite often, where at each step, you're going to take your hypothesis, pick a random subtree in it, and resample a new one from the prior. And so this gives us some way of navigating the space. But for nearly every program in our hypothesis space, we have likelihood 0. So MCMC doesn't really get any help from this likelihood for figuring out if it's on the right track. And a common approach in prior work is to basically come up with a kind of ad hoc smoothed likelihood function that is going to put a bit more mass on programs that produce outputs that are similar by some ad hoc type specific distance metric similar to the actual outputs. And so it's about changing the weights or the probabilities on these existing programs. And in contrast, that can be useful, but relies a lot on developing the specific distance metric and how well that distance metric actually guides us towards these solutions. And in this work, we're going to take a different approach. We're going to extend the hypothesis space to include probabilistic programs in addition to deterministic ones. So we aren't reweighting any of the deterministic ones. We're just adding these probabilistic programs that can naturally have probabilities between 0 and 1 because they can have some probability of producing the output. And the goal is that these are going to make our space a bit more well-connected and help us on our way to finding these deterministic programs. And so what do we mean by extending the space with these probabilistic programs? Well, if we just take our grammar from before and we add some random primitives to it, then given some input-output examples and any hypothesized programs, we can go ahead and evaluate likelihoods. Evaluate the likelihoods that those programs produce those outputs when run on those inputs. And these three programs in the middle, for example, all involve a singleton list of some kind. And so they all end up producing, with random contents that all ends up ascribing different non-zero likelihoods to these, or to the input-output examples. Now, the idea is that we can run our MCMC algorithm in a space that includes all these probabilistic programs. And instead of something like an ad hoc edit distance-based likelihood, we'll just use this exact same generative model that we had before. So yeah, except that now, when we actually evaluate a program, the likelihood is not necessarily between 0 and 1 because these are probabilistic programs. And like before, MCMC is going to do this process of repeatedly resampling subtrees and accepting or rejecting proposals. But one thing to note is that in order to compute the acceptance probabilities for our Metropolis-Hastings ratios, we're going to need to compute the likelihood. And that is, we're going to need to compute the probability that these programs produce the particular outputs we observed. And this itself is a hard inference problem because it involves reasoning over the deterministic logic within the program as well as the probabilistic parts. And these are recursive, sometimes higher order functions. And this challenge actually motivated the development of a language called Pluck that we presented this summer at PLDI for tackling specifically this kind of exact marginal inference problem efficiently. And this algorithm uses lazy knowledge compilation, which is a new approach to solving problems for these kinds of discrete probabilistic programs. So what does this actually buy us? Well, we find that in practice, it gives us a huge boost. So here's a graph with the y-axis being the average number of tasks solved in a data set of these list manipulation problems. And the x-axis is the number of steps of MCMC. And here is that naive deterministic 0 or 1 baseline. The green one is the smoothed likelihood with an edit distance, and our method with probabilistic programs outperforms these two pretty considerably. And okay, but what do these trajectories actually look like? Why is this succeeding? Well, when we dig in, we find that the trajectories often involve a lot of wandering around with like a few key moments of big breakthroughs. So for example, here's a task where the solution is a function that increments odd numbers and decrements evens. And we might start with a very general hypothesis, like, oh, it's some random list of numbers, which, after wandering around a bit, there's a breakthrough of kind of refining this to, say, a map over the input list that generates random numbers for each element. So this is going to give much higher likelihood to our examples because samples from this are always getting the correct length. And so on, there's this process of, at each point, replacing some probabilistic part of the program with a chunk of more deterministic code. And so we're really interested, after seeing this, on if some insights from here could give us a new algorithm that solves this more efficiently. Because MCMC here is spending kind of a lot of time wandering around the space of kind of semantically equivalent things. And it'd be nice to just kind of jump through these steps. And so I don't have time to go into much detail on this, but we developed an SMC algorithm based on this idea of refining probabilistic primitives to bring in a bit more deterministic structure. So we've got, just to sketch it out, a population of particles. And at each step, we run a proposal that takes one of these and transforms it. In particular, the procedure is, given a hypothesis, we choose one of the random primitives and sample a replacement for it. We then can score our hypotheses with the same likelihood function as before, and finally resample to and continue in the normal way with SMC. And indeed, this does end up helping quite a bit. Makes the whole thing around 6 times faster on those benchmarks. And there's lots more details that I'd love to discuss offline. But yeah, thank you so much.
Thanks very much. We have time for a very short question.
And maybe the next speaker can come.
Thank you for the great talk. Did you ever notice garden pathing phenomena in your trajectory refinements? Did you ever get the chain gets stuck at the wrong part of the space because it introduced randomness at the wrong part, and now it has to make a huge edit to undo that?
Yeah. So that's a really interesting question. Right. Ultimately, these. Okay, I see, yeah. Right, that can happen, especially because, right, ultimately the likelihood here is a heuristic. We aren't magically solving the whole search problem. And so, right, it's definitely possible to kind of greedily go down one path and then learn that, that you sort of need to backtrack or do something else. And this is why we have a sort of array of particles. We do have some thoughts on theory for where this would be optimal, or just sort of more theoretical justifications for this as an approximation of something that's optimal, which I'd be very down to chat